Hey everyone, and welcome. So today we're going to dig into something we all became very familiar with, the face mask. But we're going way beyond the basics to look at the pretty amazing physics that makes them actually work. It's way cooler than you might think. Let's get into it.
Right? We all wore them. But let's be honest. If someone asked you to explain, step by step, how a piece of fabric stops a virus particle that's 1,000 times smaller than a grain of sand, could you do it? Well, the answer is a lot more complex and, frankly, a lot more fascinating than you'd expect.
So, to really get this, we first have to understand that every single mask is actually trying to do two totally different but equally critical jobs at the exact same time.
First up, you've got what's called source control. This is all about protecting other people from you. It's designed to trap the tiny respiratory droplets you breathe out. And this is a huge deal because we know that more than half of all transmissions come from people who don't even have symptoms. Then, on the flip side, you have wearer protection. That's the part that protects you by filtering the air you're breathing in.
Okay, so how does that filtering actually happen? This is where a really common misconception comes into play. You see, most of us kind of think a mask works like, well, a tiny screen or maybe a pasta strainer.
Yeah, the idea is pretty simple, right? The holes in the mask material are just smaller than the virus particles, so the particles can't get through. I mean, it makes perfect sense on the surface. But that's not the whole story. It's not even the most important part of the story.
The truth is so much cooler. The fibers inside a really good filter, like an N95, aren't a neat little screen. They're a chaotic, tangled mess, like a microscopic jungle. And they are specifically designed to catch particles that are way smaller than the gaps between the fibers. So how on earth is that possible?
Well, it's not about just blocking things. It all comes down to physics. There are these invisible forces that work on that microscopic level that turn that tangled web of fibers into an incredibly effective particle trap.
Turns out there are four main physical mechanisms that let these fibers snatch particles right out of the air: inertial impaction, interception, diffusion, and electrostatic attraction. Let's break down a few of the big ones, starting with the largest particles.
First, we've got inertial impaction. This works best on bigger, heavier particles. Okay, think of it like this. Imagine you're in a car going really fast, and you come to a super sharp turn. You can't make it, right? Your momentum, your inertia, carries you straight ahead. It's the same thing here. As the air snakes around a fiber, a big particle just can't make that turn. It keeps going straight and bam! Slams right into the fiber and gets stuck.
Now, what about the absolute smallest particles? The really, really tiny ones. This is where things get weird. A totally different principle called diffusion takes over. These particles are so incredibly small and light that the air molecules themselves are constantly knocking them around, like a pinball. So they don't fly in a straight line with the air at all. They just sort of zigzag and wander around randomly until, they wander right into a fiber and stick. And this is the secret weapon, especially in N95 and surgical masks. It's called electrostatic attraction. The fibers in these filters are given a static charge. You know how a sock just sticks to a sweater when you pull it out of the dryer? It's exactly like that. The charged fibers act like little magnets, literally pulling particles out of the airstream toward them. It's an active capture system, not just a passive net.
So this all leads to this really interesting idea of a Goldilocks particle. See, particles that are around 0.3 microns in size are in this tricky middle ground. They're too small to have enough inertia for impaction to work well, but they're too big to get bounced around randomly by diffusion. They are by far the hardest particle size to catch. And that is exactly why N95 masks are tested with 0.3 micron particles. Because if a mask can stop those, it's even better at stopping the particles that are much bigger and much smaller. Okay, so we have this incredible technology, all based on some pretty mind-bending physics. But all of that brilliant science can be completely defeated by one very simple, very human problem.
And this quote from the research really says it all. The filter material can be practically perfect, but if it doesn't form a tight seal against your face, its actual effectiveness just plummets.
And just how much does a tiny gap matter? The data is kind of shocking. A leak that's just 1.5 square millimeters, that is smaller than the head of a pin, can cut the protection you get from an N95 respirator in half. Because air is just like water. It's lazy. It will always take the path of least resistance.
So this is the key takeaway, the difference between material efficiency and fitted efficiency. In a lab, the material itself might be 95% effective, but in the real world, if it doesn't seal to your face, air just rushes in and out through the gaps around your nose, your cheeks, your chin. And that can drop your actual protection by 60% or even more. The fit is not a small detail. The fit is everything.
All right, now for one last really surprising twist in this whole story. It turns out that the moisture from your own breath has a really powerful and completely opposite effect on different kinds of masks.
For a simple cotton mask, your breath is actually a huge help. See, cotton is hydrophilic. It loves water. It soaks up the moisture from your breath. This makes particles that pass through get damp, swell up, and become bigger and easier to trap. But for those N95s with a special electrostatic charge, high humidity can actually be a bit of a hindrance. Over time, all that moisture can cause that critical static charge to slowly fade away, which can slightly reduce its efficiency.
And we're not talking about a tiny effect here. Just look at this data. In lab tests, a cotton flannel mask's filtration efficiency skyrockets from just 12% when it's dry all the way up to 45% in humid, breath-like conditions. That is almost a four-fold jump in performance, just from adding a little moisture. Pretty wild, right?
So we've peeled back the curtain on the invisible physics, we've seen why fit is absolutely king, and we've even uncovered the strange role our own breath plays. It really all leads to one big question. Now that we know all this, what will the next generation of masks even look like? How can we engineer them to be even smarter, fit better, and protect us more effectively? The science is always moving forward, and you can bet the technology will too.